We did a little sound check here. I might turn the volume up here on my computer for half a second, but this is what we're going to be doing. We're going to be looking at real-time amperage draw on a circuit. We're going to be looking at the code book. We're going to be diving into multi-wire branch circuits and ampacity, and we're going to be doing some practice test stuff in the National Electric Code book. So this all stems from this comment here. This is the comment. And it says, you are telling people something that is not true. You may want to look at the code book. So we're going to do just that. We're going to look at the code book. Let me turn the volume up and do a sound check. Hang on. If you guys can hear me, let me know in the comments below. That would probably be good too. Because according to everything that I see, we should have sound. Although I didn't hear it on my laptop. Oh, there we go. Shut up. Awesome. Cool. We can be heard. I guess. All right, so first thing. Cool. All right, so what we're going to do, we're going to plug this into a receptacle live, and we're going to look at the amperage coming off of this. This is going to be on a Milwaukee charger, and we're going to examine that there's current on the hot and also current on the neutral. So that's what we're going to do. You actually look like Adam Sandler. I appreciate it, man. I don't know if that's a compliment or what, but nothing I can do about it. So just so you guys know, this is a really fast way to wire a receptacle. And yes, we are putting the neutral on the hot. It doesn't matter. We're just doing this for testing purposes. But look, you can wrap that really quickly just by doing that. So this on here. We just got to tighten these in. We're going to plug it into a receptacle here and get this going. One of the first comments is that the neutral only carries the imbalance. And also the neutral flows to ground or something crazy like that. So we got to show people not to just read the comments, because a lot of good information is from the comments, and that's usually where I get most of my best information for videos. But in this case, some of the comments on this one video are just so wrong that we got to stop what we're doing and actually set it straight. So do not do this at home. This is a live receptacle. I'll show you this now. So, see here? I don't know if you can see the red. It's pretty bright in here. There's a red there. See, there's a live receptacle. So what we're going to do, I'm going to wrap this around my microphone. Would be a mistake to wrap that around. I'm going to put this around my DeWalt drill. Make sure nobody gets hurt. Maybe someone's feelings will get hurt. Who knows? All right, so the hot is here. Yeah, someone's feelings definitely going to get hurt. Okay, hot is here, so we're going to plug that into the hot. Neutral's here. We're going to go far down here. And The Milwaukee charger is now on. Now I'd like to get this in here a little more. We might strip back something. I'm going to grab the phone. Hang on, because this is just a little bit kind of sketchy. Let me strip off a little bit more insulation. Remember, this is hot, not this. And I'm going to kind of put a little squirrely kind of shape on it so it stays in there better. Okay. Let's do this. Let's wrap this around the code book. Perfect. Okay. All right, so hot's going in now. The hot is in. I'm going to wrap it around this plug. Just to kind of hold it there. It can't come out. I'm going to put the neutral on the back side just to make sure. There we go. We could catch up with the chat. What's going on? Here's what the comments are right. Was adjustment. Loop circuit 120 through the neutral as well. You actually look like Adam. Okay, yeah. So what's going on? We had I don't want to say a stupid comment, but it was not a smart comment. So I guess we could call it a stupid comment, considering that I got the comment 20 other times and pretty much harassed saying I don't know what I'm talking about. So, you know, what else are you going to do when you got somebody calling you out other than just to prove them wrong? So neutral's going in here. Here's the neutral. Sorry, I needed more wire. It's actually a little bit scary. Okay. Dang. Hang on. If only they made a line splitter. What we need is a line splitter. But I threw my other one away. You don't know what a line splitter is. It separates your hot and your neutral. So you don't have to do this sketchy crap. Come on, please. There we go. He's going there. There we go. Okay. Okay, there we go. So, here's the Milwaukee here. We're going to plug this one in here. Let me pull this down here. There we go. We got it in the bind. Okay, perfect. Now, the Milwaukee charger is on. Okay, that's what that's plugged into. And we're separating our hot, our neutral up here, and the hot down below. And the code book is isolating. What we're going to do, we're going to grab our tester here. We're going to set this to amperage. And we're going to check the amperage here. This here, we got 2.1 amps on the neutral. That's strange. I thought the neutral only carried the imbalance. Let's see what the hot says. That's just the strangest thing, man, because this guy told me in the comments that the neutral only carries the imbalance, which is really strange to me because the comments and the internet is always right. So there's proof that the neutral does not carry the imbalance, which is just dangerous, right? So neutral does not carry the imbalance. The neutral carries the full load, and I'll draw that out in the whiteboard here in a second. But you can see here what we built and did crazy stuff with was just to split the hots and grounds. Now, they make something called an inline inverter, or I'm sorry, that's something else. They make something called an inline splitter that pretty much does the same thing and separates the wires on either side. And you can plug in your appliances to it, and it will tell you what the load of your appliances is. It's a lot easier than having to do this crap, right? But same thing. So we're going to throw this down now. And actually, honestly, 2 amps to charge a battery is, that supercharger is beefy. 2 amps on a battery to charge it, wow, that's great. That's a fast charger. Let's see here. Wish you, but I got a hot word. Nice. Let me see here. Catch up with the chat. Sean Wooka. I'm Russian visiting USA for a bit. Nice. Welcome. My dad made a couple. Didn't work for some reason. I'm going to have to catch up with the chat again, maybe? Maybe the line splitter. Maybe it didn't work. Okay. So now what we got to look at is, does the neutral flow to ground? Can't quite show you that, but you got to understand the whole point of the ground. So the ground and the neutral are the same, but the neutral does not flow to ground. The neutral flows back to the source, which is a transformer. It's probably not even worth me drawing that out. But what I can read you in the code book, because that's what the comment said, read your code book. So let's look back at the comment. That, actually, I can probably bring it up on the TV. What is TV new? Okay. The chat's way over there. Whatever. We're doing here. He says, wrong, dude. The neutral is not counted for the purpose of derating. The neutral is grounded conductor that takes the imbalance of the circuit. Well, we just proved that wrong. So there's that. If you read your code book, it clearly explains it very well. More to the point, through the neutral is considered a current carrying conductor. It is the ground conductor. What? Let me read this again because I haven't read this comment actually. It says, if you read the code book, it explains it very well. More to the point, through the neutral is not considered a current carrying conductor. It is the grounded conductor. Yeah, that's true. And it's grounded. Let's see what he says here. Sometimes it's called the return or the reference to ground. It is a conductor, but it's not called the current carrying conductor. The code book refers to it specifically as the grounded conductor for the purpose of derating the neutral. And first off, there's no such thing as derating. You've got corrections and adjustments. So derating is what we used to call it before we became educated. So you've got corrections, which has to do with temperature. And then you've got adjustments, which has to do with the number of wires in the pipe. So if we want to entertain that idea, we can go over here to the rules for neutrals. And it says the neutral conductor shall be considered current carrying in accordance with the following. So right off the bat, we know that the neutral is considered current carrying. I'm trying to adjust this microphone. Where you would not consider the neutral current carrying would be if you had a multi-wire branch circuit. So let's look at that. I'm going to try and keep the camera as still as possible. A neutral conductor that carries only the unbalanced current from the other conductors of the same circuit shall not be required to be counted when applying the provisions. Okay? A neutral that's carrying the only the unbalance of the same circuit would be like this. It'd be a multi-wire branch circuit. So, oh my God. So if you had, I'm just going to draw very simple for you guys to make it very, very simple. If this is your breaker, okay, and you got wires coming off of your breaker, and it feeds 3 different lines here, like this. That's your hot. Add circuit 1, 3, and 5. And inside of here we have a neutral bar. Is there a neutral bar? And you have 1 wire. And all this is in a junction box, by the way. We put all these wires in one junction box. So this is the junction box, or the conduit, however you want to look at it. And the neutral connected each one of these. This would be the example of the neutral carrying only the unbalance of the conductors. Now the rules for this would be if you put a handle tie here, you would have to simultaneously disconnect all 3 of these. That way, if somebody is working on circuit 1, they're not getting current from circuit 3 and circuit 5 backwards on the neutral. I just realized I'm not talking to the mic. Sorry. Hopefully you can hear me. Maybe I should start over. 1, 3, and 5 is the circuit. This is circuit 1, 3, and 5. This is a total circuit. This is a multi-wire branch circuit. This is the neutral for this circuit. This is considered one circuit. So when it says conductors of the same circuit, these are the conductors of the same circuit. This is the neutral that carries only the imbalance of this circuit. This is a multi-wire branch circuit. If you've done what we did, and we have a circuit in series where we had this, and it was a 120 volt circuit, it would look like this. We can add another breaker. This would be circuit 7. It would come here. It would go to the receptacle, and you'd have a return path. And when you put your multimeter on this circuit, like we did, if we wanted to draw the jaws, that is terrible. If we were to do that, this was 2 amps in on the hot, because we had the load on there. That was the load. And if we put the multimeter here with the jaws like we did, that was also 2 amps. That's not the imbalance. That's the full circuit. This is a series circuit. So back to the code here where it talks about multi-wire branch circuits, where this circuit and the neutral carries only the imbalance, that's where you do not count this neutral. Would be on a multi-wire branch circuit where the neutral shares on the same circuit. So let's look at the verbiage again. A neutral conductor that carries only the unbalanced current from the other conductors. Other conductors would be key here because obviously you can't have conductors if you just got one circuit, right? So neutral conductor carries only unbalanced current from the other conductors of the same circuit. These are the conductors of the same circuit. This is a neutral that carries only the imbalance. AG. And then you got this, 3-wire circuit. If it's 240 volt and you got a neutral on it, that's going to carry the same current. So that's current carrying. That's the neutral current carrying. And then you got a 4-wire 3-phase circuit where the major portion of the load consists of nonlinear loads. Harmonic currents are present in the neutral conductor. The neutral conductor, therefore, is considered current carrying. That's where if you had a 4-wire 3-phase circuit like this, But these loads here are heavy on neutral. That's where this neutral is going to be counting as fully current carrying. So everyday situation down here, which is what the video was essentially, was a single phase 120 volt circuit. The neutral does not carry the imbalance. So you count it as current carrying, as you should, because we just demonstrated it on the multimeter. Let's see what else this comment says, because we want to remain respectful, but also respectfully, you're wrong. Let's see here. I can't even read it. Control plus? Dang, I can't read it. It says here, I had to read it through the phone. If you read the code book, it explains it very well. More to the point, the neutral conductor is considered current carrying conductor. It is a grounded conductor, sometimes return reference to ground. If the conductor, but not called current carrying conductor, the code book refers to specifically as a grounded conductor for the purpose of derating the neutral. It is not counted as a current carrying conductor when the current carrying conductor are derated. Neutrals are also made the same size as the larger current carrying conductors. In other words, if you have 7 or more current carrying conductors, then those, you can see where this looks really convincing, I suppose, to the average person. Seven more current carrying conductors, those are the ones counted, not the neutrals. So there are 7 current carrying conductors, not 14 in said conduit. This means you have to take 75%. 75% is 70. Anyway, we'll ignore that part. 75% of the full ampacity of the wire you're using. At no point have I said that the neutral doesn't carry current. It does. It carries the imbalance, as I stated earlier. Doing things the way you're saying means you're wasting money on bigger wire and possibly bigger conduit. It won't hurt anything, but it's a waste of money and not necessary. Well, okay. First off, it's not 75%. So if he's wrong there, he's probably wrong everywhere else, right? It is 70%. First off. Next off, we just showed you where you have 2 amps on the hot and 2 amps on the neutral. Actually, I'll scroll backwards so we can see it. I'm going up here. See here. Hang on. Bear with me. There. So there's a live receptacle. So what we're going to do, I'm going to wrap this around now on. Now I'd like to get this in here a little more. Let's strip back to chat. What's going on? 20 on the neutral. That's strange. But the neutral only carried the inbound. Let's see what the hot says. But that's just the strangest thing, man, because this guy told me in the comments that the neutral only carries the inbound, which is really strange to me because the comments and the internet is always right. So there you go. The neutral doesn't carry the imbalance. I think I should keep reading, though. Or I think I was done reading. I think you should read articles 200 through 400. Nice. If I only knew he was live and on blast. Let's see here. Misha, thank you for everything you do. It helps me every apprentice to learn a little at a time. Oh, yeah. Also, I tried following my dad's steps, but it didn't work. I think it worked. Let's see here. Yeah. So, we're giving away a little tool pouch. I might throw some tools in there too. I'm going to announce the winner probably tomorrow during a live, and we'll do the poll. We'll do it live. We'll put all the names in the hat. I got to see you commented on the video. See what apprentice is going to win. But pretty much everybody with a thumbs up in that one video is going to be entered. So that'll be something coming up. But Yeah, I mean, you got a 120 volt circuit. It's essentially in series, right? So I don't know how much math or how much of a nerd you guys are, but if you do like the reciprocals where you're taking a parallel circuit and you're trying to figure out what the number is when you have multiple different ohm ratings and things like that, that's essentially what's happening when you're sharing the neutral, because it's carrying the imbalance, not carrying the full load. And that's when you don't count the neutral. But in this case, in a series circuit where you've got 120 volts here, you got your load in series and the neutral's coming straight out, that neutral is going to be carrying the full load current, which is current carrying. So you count it. So if we were to look at that, we would look like this. We would have, well, let's look at the video. Let's look at the video. Okay, so we got 12 there. We had 1, 2, 3, 4, 5. We have 5 neutrals, which is not enough, by the way. 1, 2, 3, 4, 5, 6, 7. I think I counted 12 hots. So 12 hots and 12 neutrals carrying the full load would be 24, which wouldn't even be 50%. It would actually be 45%. So what you would do is you would take, and what you're allowed to do, you're actually allowed to use a 90-degree C column, which, let me see if I can find that rule for you real quick. Back one. Hang on. This is the adjustment factors here. And if you look here, it says that we can use the 90-degree C column in the rules in here. I don't want to put myself on blast here trying to find it. But you can use the 90. I'll have to find it. I'll post it later. There's not very many places you're allowed to use the 90, but this is one of them. So we're going to use the 90. And if we look at number 12 on 90-degree C, you'll see that it's 30 amps, I believe. Yeah, 30 amps. So 45% is less than 15. So if you look here, we go to 240.6. Right here. You'll see that 15 is a standard size, also the smallest size. So the biggest that you can put this on would be a 15 amp breaker. Now you could up the wire size, which is what you should do, to number 10, and that would get you at least 40, which would be like 16, 17 amps once you do 45% on it. One more. So if we did number 10 is 40, 50% is 20. So 45 is like 17.5, something like that. Now we can put this on a 20 amp breaker, but you got to put number 10 on it, which is why I always ran number 10. 1-inch conduit, number 10, 13 conductors, 6 hots, 6 neutrals, and you could go like 100 feet away. Voltage drop, everything in there. But yeah, that's that. We could also do, I was planning on doing some more questions for you guys. If we went up here, we could keep going with this if you guys want. When conductors are installed in a conduit or tubing, the nipple of, and we know the answer, we already know the answer here, because we're just doing this. So strange. Check it out. Right here. There's rules in here for this. So if we go back here, more than 3, you're going to see some exceptions. So we're looking for an exception. And it's right here. Adjustment factors shall not apply to conductors having a length of not exceeding 24 inches. So that's going to be the answer there. But how do we find that answer? Well, adjustment factors would be a good way to, start looking. So you see the word adjustment factors. You should know by now where adjustment factors is, but that same code is actually in the back of the book in chapter 9, table 8, where it talks about, can I say nipples? Chapter 9, that's the annex. Right here. One more, back. One more forward. There we go. I'm right here, 24 inches right there. Conduits or tubing nipples having a maximum length and not to exceed 24 inches. So this right here, you can see you got the conduit tubing right there. So we've got it in this portion of the code, and then you've also got it in the 310. This looks like it might be in an appliances. Got air conditioners, go to appliances, look that up. ASMR. What's up, Joey? So anyway, yeah, I thought I'd just show you guys, 120 volt circuit. The neutral's pulling the same amount of current as the hot. It doesn't carry the imbalance. Oh, as far as it going to ground, let's talk about that. We're going to go to 250. The only reason why the ground exists is to get current back to the neutral. So the current doesn't flow to ground. If you guys understand that, you'll respect electricity that much more. And you'll want to actually install all of your bonding screws, bonding jumpers, all that stuff. So if we go here to the beginning of 250, like the very beginning, it's fascinating, the similarities between DC and AC. At the same time, the big difference is, yeah, exactly, AG. All right, so here we go. The very beginning of grounding and bonding talks about all the electrodes. This is like the most important code in the whole book. So if we look at here, the effective ground fault current path, electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance circuit facilitating the operation of the overcurrent device or ground detector for high impedance, maximum ground fault current likely to be imposed from any point in the wiring system. So what that means, I'm going to explain that here in a second. But I'll show you another one. Grounding electric, normally non-current carrying conductive materials enclosing electrical conductors or equipment or forming the part of such equipment shall be connected to the earth as to limit the voltage to ground on these materials. Now, what that means is this. I need to erase this actually. That sucks. This is what that means. Dog doesn't sound happy. We got a panel here. Okay. I'm not going to draw them all. We'll just draw the main. We'll draw the main, and we'll draw one breaker. That's one, and that's two. Figure one circuit two. And we'll draw the neutral because that's relevant. We'll draw the ground because that's very relevant. And we're also going to draw the jumper. So in this case, we're just going to do some dots to show that the ground and neutral are connected together here. We have a receptacle. We have a box. And we have the conductors going back to the panel. We have a hot, neutral, and ground coming from this receptacle. What happens is, if the hot makes its way to the case here, current gets on the ground wire. And because the neutrals and grounds are bonded together here, the current gets on the neutral. Goes up the neutral conductor. It goes through the weatherhead of your house. It goes to the transformer. And it comes back on the hot. The dogs are going crazy. I might have to go. So the only reason why you have a ground is to get current back to the neutral. The current doesn't flow back to ground. So that's the whole point in your ground, is to get current back to the neutral. Coco! Yeah, they said the current flows to ground. It doesn't do that at all. In a small way, it does in a way, but the voltage is so low that it can't. You're going to have multiple utility systems that are all grounded with a ground rod. You're going to have multiple transformers that are all grounded with a ground rod. You're going to have your house that's grounded with a ground rod. But that voltage is so low that it can't flow to each other. It's just not how it works. The reason why you have a ground is to make everything the same potential and to get current back to the neutral. That's what the ground does. There is no negative. Even on your car, your chassis is only negative, that just in case you get current on your chassis, you can trip the fuse to get back through the negative to get back to the hot. It's just not the way it works. If you did not connect your chassis to the negative in your car and you shorted something out, you would just energize the chassis of your car. It's the same thing. The neutral has nothing to do with the transformer other than it connects to the neutral, the ground, to trip over current devices, to sense ground faults, and to create the same potential. So in a way, your ground is your voltage, but everything's so grounded and bonded with ground rods that you're going to have the same voltage just about wherever you go. Like everyone says, your ground creates your voltage. That's true. If you lose your neutral, your ground will kind of stabilize and stop, fluctuations. But you still need a neutral to go back to the source. Like you're going to have some really squirrely stuff going on. The neutral does not return to ground, and it shouldn't unless you have a fault. The thought that your neutral returns to ground in a normal situation is just wrong. So there you go. Thought I'd address that comment, and we'll see you guys later.